Sometimes we run into problems where we are interested in finding the derivative of a function that is defined by an integral. Here is such a function, or this one, for example. These types of problems have not only functions inside the integral, which are the integrands, but also functions on the integral themselves, the so-called limits of integration. Here the upper limit of integration is a function of x. Here the lower one is. And in this last problem, both limits of integration are functions of x. Here's the first problem. In this problem, I'll take a minute or so to talk about the background behind the methods, so we'll take our time with this problem, but problems 2 and 3 I'll go over more quickly. The obvious thing may seem to be to take this integral first, get an answer with x in it, and then take the derivative of that answer to get the final answer. The problem with this direct method is the function inside the integral, sine of e to the t, has no known antiderivatives in closed form, so we cannot get a specific answer like that, or direct answer like that. But the function is continuous, as you can verify by taking by graphing it on a calculator or a computer. And every continuous function by the fundamental theorem of calculus has an antiderivative. So we know that there is an antiderivative. Let's call it f of t. Then that means that by the definition that f prime of t is sine of e to the t. Now the second part of the fundamental theorem says we can write the integral from 0 to x as the difference between the antiderivative evaluated at x, the upper limit, minus the antiderivative evaluated at the lower limit, 0. Now let's take the derivative of this function. We get the derivative of f of x minus the derivative of f of 0. Derivative of f of 0 is going to be 0 simply because f of 0 is a constant and the derivative of a constant is 0. Derivative of f of x, or f prime of x, is simply the function inside the integral with x plugged in. So we get this derivative of this function is just sine of e to the x. Because the derivative of f of 0, because the derivative of a constant is 0 and disappears from the final answer, the number at the bottom of the integral does not affect the derivative. So if I had 1 or 2 or minus 3 instead of 0, I would still get the same answer, sine of e to the x. Now let's think of a quantity u that may be a function of x, like ln of x, for instance. Then this integral is a function of u. So if u happens to be ln of x, then this is f of ln of x. If I take the integral with respect to u, if I take the derivative with respect to u, then just like we had before with x, we also have again with u. The derivative releases the function inside the integral and plugs in the upper limit of integration. On the other hand, we need to take the derivative with respect to x because that's what we were looking for. So if we do the derivative with respect to x, but with u still sitting up the function of x, then we are taking the derivative of with respect to x of a function u. So we use the chain rule right here, and The chain rule says the derivative with respect to x here is the derivative with respect to u times the derivative of u with respect to x. Derivative with respect to u is also same thing as f prime of u, and the u dx of course is u prime of x. Okay, after all this calculation, we have all the ingredients to solve the problem. We just figured out this equality or equation. df du is sine of e to the u, so that goes in there. Du dx, the derivative of natural log of x, is 1 over x, and that goes in there. After plugging in, we get the derivative of the integral is equal to sine of e to the u times 1 over x, and let's remember that u is natural log of x, so we plug that in. We can get a little bit of a simplification. E to the natural log of x is x because of the inverse function relations. We can sort of cancel them out, and we come up with the simpler answer, sine of x times 1 over x, or sine x divided by x, and put it all together, we get the final answer, sine of x divided by x. And let's not keep in mind that we didn't need to do any integration to get this answer. Okay, let's take a look at the second problem, where we have the function on the integral down below. In order to use the method that we just discussed, this has to come up to the upper limit. For this we use the property of integrals that says switching the order of limits of the integral is going to give us a negative sign. So we'll do that for this problem. Put x to the 4 on top, get a negative sign. Now that's our u. We get f prime of u times the derivative of u. Here, square root of x to the 4 is nothing other than square root of u. And figuring this out is easy. Square root of x to the 4 is x squared. Derivative of x to the 4 is 4x cubed. And here is the answer in a tidy way. In this particular problem, we could have done the problem directly by first actually integrating, though it's not necessary to integrate. In this case, the antiderivative is easy to get. Integral of 5 is 5t. Integral of the square root of t, or t to the 1/2, is t to the 3/2 over 3/2, which becomes like this. Then we put in x to the 4 and 1 the usual way, get an answer with x. And now if I take the derivative with respect to x of this whole thing, I'll get the same answer as in here. Now let's move down to the third problem, where both the lower and upper limits of the integral are functions. To deal with this, we use a property of integrals that says we can take any integral from a to b and write it as integral from a to some number c plus integral from c to b. C can be any third number. If I do that, if I split the integral here in the same fashion, I can pick and choose an appropriate number c. So let's just pick c equal to 0, and we get a sum of two functions or integrals. The first integral has x squared at the bottom, a number on top, so let's switch. Introduce a negative sign. The second integral is already in the correct shape. If we take the derivative, now we are back to the original problem. The derivative of the first integral plus the derivative of the second integral, and next we will figure out each of these two derivatives. Now the first of the two terms has a function u equal to x squared, so the derivative of this integral will be 1 over u squared plus 1, and that's just the same thing here with t instead of u. In other words, that's f prime of u times the derivative of u. Derivative of x squared is just 2x. So x squared being x to the 4, we get the answer 2x over x to the 4 plus 1 for the first integral. For the second integral, the function is tangent of x. Taking the derivative, we'll introduce u equal to tangent of x in here. So we get 1 over u squared plus 1, that's r f prime of u, times du dx. U is tangent of x. And so we take the derivative of tangent is secant squared, and the first term over here can be simplified. Tangent squared plus 1 works out to secant squared, and if I put that down here, I get to cancel with the secant squared in the numerator for an answer of 1. Okay, I add that to the negative of the first term to get the answer to the problem, and if we combine the fractions, we get the final answer to the problem.